Welcome to this explainer. Today, we're going to take the whole agricultural environment and turn it into a precise, measurable science. Because you see, a farm isn't just a patch of dirt where crops happen to grow, it's a completely dynamic, interconnected environmental system. Literally every single drop of water, every gust of wind, and every ray of sunlight, they're all interacting in this massive, continuous chain reaction. And that reaction, it completely dictates whether a harvest is going to thrive or fail. So to really master agricultural science, we've got to learn how to decode the language of the atmosphere. Let's get right into exactly how we track and quantify this invisible weather system.
To really understand how this system works, we'll build it out step by step. We're going to cover 5 crucial metrics today: light and solar energy, wind speed and direction, tracking atmospheric temperature, calculating relative humidity, and finally, measuring water evaporation.
All right, starting off with number 1. Light and solar energy, which is really the primary driver of the whole shebang.
You have to realize that every single atmospheric change on the farm kicks off with solar energy. Imagine drawing a basic farm scene. Right up at the top, you've got a shining sun. Now, the absolute most crucial thing to remember here is that the atmosphere isn't just static air sitting there. It's this continuous churning cycle of heat, wind, and moisture. And the engine powering that entire machine? Yep, it's the sun. That solar energy beats down, it heats the soil, it warms up the air, and it evaporates the water. Honestly, without this initial input of solar radiation, our whole weather system just wouldn't exist.
But here's the thing. Not all sunlight is exactly the same. Let's break down the exact composition of that incoming solar radiation. According to the syllabus, the energy actually reaching our farm is strictly divided into 3 distinct categories. Exactly 50% of it is visible light. That's the light the plants actually use to pull off photosynthesis. Next up, we have 45% infrared radiation. We feel that as heat, and it directly drives our temperature and our evaporation rates. And lastly, the remaining 5% is ultraviolet light. Pinning down these exact percentages is absolutely crucial because it tells us exactly how much of the sun's energy is going into heating the farm versus, actually feeding the crops.
So, how do we actually track this energy out in the field? Enter the Campbell-Stokes sunshine recorder. Think of it like this. Picture a perfectly clear, solid glass sphere sitting securely on a metal stand. As the sun slowly moves across the sky during the day, this glass sphere basically acts like a giant magnifying glass. It takes that solar radiation and focuses it right down into a single intense point of light that rests on a specially designed curved paper card right behind it. As the sun shines, that focal point literally burns a continuous trace line into the paper. If a cloud happens to pass over, the burning stops. It's that simple. By the end of the day, we can just measure the length of those burn marks on the card to figure out the exact number of uninterrupted sunshine hours the farm got. It's a brilliantly simple, totally mechanical way to record solar duration.
Moving on to part 2, wind speed and direction, or air in motion.
Okay, so as that solar radiation we just talked about heats the Earth unevenly, the hot air starts rising and cooler air rushes in to take its place. That's what creates wind. And to document this moving air, we've got to measure both its speed and its direction. Let's look at speed first. We use an instrument called an anemometer. This device has these horizontal arms, and at the end of each arm, there's a hollow cup. Because the cups catch the wind right on their open side, the entire top of the instrument gets pushed and starts rotating. Naturally, the stronger the wind blows, the faster those little cups are going to spin. That mechanical rotation is directly proportional to the wind's strength, giving us a way to perfectly quantify the wind speed, which we standardly record in kilometers per hour.
Speed is only half the equation, though. We also absolutely need to know where the wind is actually coming from. For that, we use a wind vane. This is a balanced, arrow-like pointer mounted on a vertical pole, and it rotates totally freely. Notice how the vane actually works. It's got a larger tail section that catches the breeze, which forces the tip of the arrow to point directly into the source of the wind. Down below the arrow, you have fixed crosshairs that indicate north, east, south, and west. So if the arrow is pointing north, it means we have a north wind, meaning the wind is blowing from the north. By pairing this with the anemometer, we suddenly have incredibly precise data on our farm's air in motion.
Next up, part 3, tracking atmospheric temperature. Let's talk about heat on the farm.
So sunlight and wind are constantly interacting, and together they dictate the exact temperature of the air surrounding our crops. But to measure this air temperature accurately, we can't just go and hang a thermometer out in the open. If we did, the direct solar radiation would just heat the instrument itself, and boom, we get a false reading. We want the temperature of the air, not the sun's direct heat, right? So this brings us to the Stephenson screen. Let's walk through its strict design requirements.
First off, it's a wooden box elevated exactly 1.2 to 1.5 meters off the ground. That keeps it safely away from any heat radiating back up off the soil. Second, it's painted a bright, stark white to reflect that incoming solar radiation. Third, the sides are louvered. That means they have these angled wooden slats that allow natural wind to circulate through, but keep the rain and sun out. And finally, the doors are specifically hinged so they open away from the equator. This is super important because it guarantees that when a farmer opens the box to check the readings, direct sunlight never actually strikes the sensitive instruments inside.
Okay, so what exactly is hiding inside that Stevenson screen? Well, we use two very distinct instruments to capture the daily temperature extremes. First, we have the maximum thermometer. This one uses mercury. As the day heats up, the mercury expands and gets pushed up the tube. But right near the bottom bulb, there's a tiny, narrow constriction. When the temperature eventually drops later in the day, that constriction actually breaks the thread of mercury, so the liquid can't fall back down. It literally stays frozen right at the absolute highest temperature of the day. Then, right next to it, we have the minimum thermometer. Now this one uses alcohol, which is clear. And inside that alcohol, there's this tiny dumbbell-shaped sliding marker. As the air cools down at night, the alcohol contracts and moves down the tube, dragging that little marker along with it because of surface tension. When the sun comes up and the temperature rises again, the alcohol just flows right past the marker, leaving it sitting exactly at the lowest temperature point of the night. Pretty clever, right? Together, these two thermometers give us the perfect thermal boundaries for our farm's entire day. Let's keep moving. Part 4. Calculating relative humidity, or moisture in the air.
Temperature directly controls exactly how much invisible water vapor the air can physically hold. The strict textbook definition of relative humidity is the actual amount of water vapor present in the atmosphere expressed as a percentage of the maximum amount of water that the air could possibly hold at that specific temperature. You see, warm air can hold significantly more water vapor than cold air. If the air is holding exactly half of what it's capable of holding, then the relative humidity is exactly 50%. And to measure this out in the real world, we use a device called a wet and dry bulb hygrometer.
Let's take a look at how this instrument actually generates data. The hygrometer is basically made up of two standard thermometers. One is just your normal dry bulb that measures the regular air temperature. But the other one is a wet bulb. Its base is wrapped tightly in a piece of muslin cloth that is kept continuously wet by dipping into a small little reservoir of water. Now, because evaporation causes cooling, that wet bulb is almost always going to read a lower temperature than the dry bulb. This brilliantly illustrates our environment in action. Think about it. The drier the air is, the faster water evaporates from that muslin cloth, which means the cooler the wet bulb gets. By comparing these two readings, we can use a standard lookup table to easily find our exact humidity. Let's trace the exact mathematical steps you'd see in your syllabus, just as if we were solving a problem together for an exam. Step 1. We record the dry bulb temperature. Let's say it comes out to 30 degrees Celsius. Step 2. We check the wet bulb, and let's say that one reads 28 degrees Celsius. Step 3. We calculate the depression, which is just a fancy way of saying the difference between the two. 30 minus 28 gives us a difference of 2 degrees. Finally, Step 4. We take that 2-degree difference and simply cross-reference it with our standard meteorological chart against the 30-degree dry bulb temp. Looking at the chart reveals that our exact relative humidity is 85%. It's a completely straightforward, logical progression from raw thermometer data to a standardized moisture percentage.
Which brings us to our final metric, Part 5, measuring water evaporation, or calculating water loss.
So the sun, the wind, the temperature, and the humidity, they all combine to exert this invisible force on our farm, constantly pulling moisture right out of the soil, a process we call evaporation. To precisely measure how much water the atmosphere is literally demanding from our crops, we use a highly standard tool called the Class A evaporation pan. Let's outline its strict physical dimensions. It's this large cylinder made entirely of galvanized iron. It has to be exactly 120 centimeters in diameter and 25.4 centimeters deep. And importantly, it doesn't just sit directly on the dirt. Instead, it gets elevated exactly 15 centimeters off the ground on a slatted wooden pallet. This allows air to circulate underneath and prevents any heat radiating from the soil from interfering with the water. Inside this pan of water, we have what's called a still well to keep the water surface nice and calm from the wind, alongside a highly precise hook gauge measuring tool to read the exact water level.
Operating this pan is actually incredibly simple, but the data it gives us, it's invaluable. Every single day at the exact same time, we calculate the water loss. Let's walk through that quick calculation. Step 1. You note the previous day's water level using your hook gauge. Let's just say yesterday it was filled up to 180 millimeters. Step 2. You go out and check the current day's level. Today it reads 175 millimeters. Step 3, you just subtract the current level from the previous level. 180 millimeters minus 175 millimeters, and step 4 gives us our result. We've experienced exactly 5 millimeters of total daily evaporation. That is precisely how much water the sun, the wind, and the dry air stole from our farm over the last 24 hours.
And honestly, this brilliantly illustrates exactly why we bother measuring all of this in the first place. We started the day with visible light and infrared heat pouring down from the sun. We saw how that uneven heating drove the wind, which we tracked with our anemometer. We watched that wind and sun affect the temperatures safely recorded inside our Stevenson screen, which then dictated the air's capacity to hold water on our hygrometer. And all of that ultimately resulted in exactly 5 millimeters of water disappearing from our evaporation pan. So here's what you really need to take away from this, and the question I want to leave you with today. Knowing this entire unbroken chain of weather data, how are you going to use these exact isolated textbook metrics to make real-world decisions? How will you use that precise 5 millimeter evaporation deficit to perfectly time your farm's irrigation schedules and absolutely guarantee your crop's survival? Think about that as you review your notes. Thank you so much for joining me for this explainer. Keep studying hard, and I'll see you next time.